Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will be discussing about Ethernet. Let's start. You can recall that TCP/IP protocol suite does not define any protocol for the data link or the physical layer. It accepts any protocol at these layers that can provide services to the network layer. Data link and physical layer are actually the territory of the local and wide area network. In the 1980s and the 1990s, several different types of LANs were used. All of these LANs use a media access method to solve the problem of sharing the media. The Ethernet uses the CSMA/CD approach. The token ring, the token bus, and FDDI use the token passing approach. Almost every LAN except the Ethernet has disappeared from the marketplace because Ethernet was able to update itself to meet the needs of the time. In 1985, the Computer Society of the IEEE started a project called Project 802 set standards to enable intercommunication among equipment from a variety of manufacturers. Project 802 does not seek to replace any part of the OSI model or TCP/IP protocol suite. Instead, it is a way of specifying functions of the physical layer and the data link layer of major LAN protocols. It was adopted by ANSI and ISO. The IEEE has subdivided the data link layer into two sublayers: Logical Link Control, or LLC, and Media Access Control, or MAC. IEEE has also created several physical layer standards for different LAN protocols. Here is the relationship of the 802 standard to the TCP/IP protocol suite. The original Ethernet was created in 1976 by Robert Metcalfe and David Boggs at Xerox Palo Alto Research Center. Since then, it has gone through different generations. Standard Ethernet, which has 10 Mbps, Fast Ethernet, which has 100 Mbps, Gigabit Ethernet, and 10 Gigabit Ethernet. We refer to the original Ethernet technology with the data rate of 10 megabits per second as the standard Ethernet, or 802.3. Although most implementations have moved to other technologies in the Ethernet evolution, there are some features of the standard Ethernet that have not changed during the evolution. Some characteristics of the standard Ethernet is that it is connectionless and unreliable. Ethernet provides a connectionless service, which means each frame sent is independent of the previous or next frame. Ethernet has no connection establishment or connection termination phases. The sender sends a frame whenever it has it. The receiver may or may not be ready for it. The sender may overwhelm the receiver with frames, which may result in dropping frames. If a frame drops, the sender will not know about it. Since IP, which is using the service of Ethernet, is also connectionless, it will not know about it either. If the transport layer is also a connectionless protocol, such as UDP, the frame is lost and salvation may only come from the application layer. However, if the transport layer is TCP, the sender TCP does not receive acknowledgement for its segment and sends it again. Ethernet is also unreliable like IP and UDP. If a frame is corrupted during transmission and the receivers find out about the corruption, which has a high level of probability of happening because of the CRC32, the receiver drops the frame silently. It is the duty of high-level protocols to find about it. The Ethernet frame contains 7 fields as shown here. The preamble field contains 7 bytes or 56 bits of alternating zeros and ones that alert the receiving system to the coming frame and enable it to synchronize its clock if it's out of synchronization. The pattern provides only an alert and a timing pulse. The 56-bit pattern allows the station to miss some bits at the beginning of the frame. The preamble is actually added at the physical layer and is not formally part of the frame. The start frame delimiter field is a 1-byte field with pattern 10101011, which signals the beginning of the frame. The SFD warns the station or stations that this is the last chance for synchronization. The last 2 bits alert the receiver that the next field is the destination. This field is actually a flag that defines the beginning of the frame. We need to remember that an Ethernet frame is a variable length frame. It needs a flag to define the beginning of the frame. The SFD field is also added at the physical layer. The destination address field is 6 bytes or 48 bits and contains the link layer address of the destination station or stations to receive the packet. The source address field is also 6 bytes and contains the link layer address of the sender of the packet. The length or type field defines the upper layer protocol whose packet is encapsulated in the frame. This protocol can be IP, ARP, OSPF, and so on. In other words, it serves the same purpose as the protocol field in a datagram and the port number in a segment or user datagram. It is used for multiplexing and demultiplexing. The data field carries data encapsulated from the upper layer protocols. It is a minimum of 46 and a maximum of 1500 bytes. The CRC field contains error detection information. The CRC is calculated over the address, types, and data field. Ethernet has imposed restrictions on both the minimum and maximum lengths of a frame. The minimum length restriction is required for the correct operation of CSMA/CD. An Ethernet frame needs to have a minimum length of 512 bits or 64 bytes. Part of this length is the header and the trailer. If we count 18 bytes of header and trailer, then the minimum length of data from the upper layer is 46 bytes. If the upper layer is less than 46 bytes, padding is added to make the difference. The standard defines the maximum length of a frame as 1518 bytes. If we subtract the 18 bytes of header and trailer, the maximum length of the payload is 1500 bytes. The maximum length restriction has two historical reasons. First, memory was expensive when Ethernet was designed. A maximum length restriction helped to reduce the size of the buffer. Second, maximum length restriction prevents one station from monopolizing the shared medium, blocking other stations that have data to send. Each station on an Ethernet network has its own network interface card. The NIC fits inside the station and provides the station with a link layer address. The Ethernet address is 6 bytes or 48 bits, normally written in hexadecimal notation with a colon between the bytes. A source address is always a unicast address. The frame comes from only one station. The destination address, however, can be unicast, multicast, or broadcast. If the least significant bit of the first byte in a destination is 0, the address is unicast. Otherwise, it is multicast. The broadcast address is a special case of the multicast address. The recipients are all the stations on the LAN. A broadcast destination address is 48 ones. The way the addresses are sent out online is different from the way they are written in hexadecimal notation. The transmission is left to right, byte by byte. However, for each byte, the least significant bit is sent first, and the most significant bit is sent last. This means that the bit that defines an address as unicast or multicast arrives first at the receiver. This helps the receiver to immediately know if the packet is unicast or multicast. Standard Ethernet uses one persistent CSMA/CD. For the physical implementation, it uses digital signaling or baseband at 10 megabits per second. It also uses the Manchester encoding. The standard Ethernet defined several implementations, but only 4 of them became popular during the 1980s. 10 base 5, 10 base 2, 10 base T, and 10 base F. In the nomenclature 10 base X, the number defines the data rate, which is 10 Mbps. The term base means baseband signal, and X approximately defines either the maximum size of the cable in 100 meters or the type of cable. The first implementation is called 10 base 5 Thick Ethernet or ThickNet. The nickname derives from the size of the cable, which is roughly the size of a garden hose and too stiff to bend with your hands. 10 base 5 was the first Ethernet specification to use a bus topology with an external transceiver connected via a tap to a thick coaxial cable. The transceiver is responsible for transmitting, receiving, and detecting collisions. The transceiver is connected to the station via a transceiver cable that provides separate paths for sending and receiving. This means that collision can only happen in the coaxial cable. The maximum length of the coaxial cable must not exceed 500 meters. Otherwise, there is excessive degradation of the signal. If a length of more than 500 meters is needed, up to 5 segments, each a maximum of 500 meters, can be connected using repeaters. The second implementation, the 802.3a standard, is also called 10 base 2, Thin Ethernet, or CheaperNet. 10 base 2 also uses a bus topology. but the cable is much thinner and more flexible. The cable can be bent to pass very close to the stations. In this case, the transceiver is normally part of the network interface card, which is installed inside the station. Note that the collision here occurs in the thin coaxial cable. This implementation is more cost-effective than 10 base 5 because thin coaxial cable is less expensive than thick coaxial, and the T connections are much cheaper than taps. Installation is simpler because the thin coaxial cable is very flexible. However, the length of each segment cannot exceed 185 meters due to the high level of attenuation in thin coaxial cable. The third implementation is 802.3i standard called 10 base T or Twisted Pair Ethernet. 10 base T uses a physical star topology. The stations are connected to a hub via two pairs of twisted cable. Note that two pairs of twisted cable create two paths between the station and the hub. Any collision here happens in the hub. Compared to 10 base 5 or 10 base 2, we can see that the hub actually replaces the coaxial cable as far as a collision is concerned. The maximum length of a twisted cable here is defined as 100 meters to minimize the effect of attenuation in the twisted cable. Although there are several types of optical fiber 10 Mbps Ethernet, the most common is the 802.3J standard, or 10 base F. 10 base F uses a star topology to connect stations to a hub. The stations are connected to the hub using two fiber optic cables. The maximum length is 2 kilometers. It is used in environments that are electronically noisy. Here is the summary for standard Ethernet. The first step in the Ethernet evolution was the division of LAN by bridges. A bridge is a network device that connects multiple network segments. It uses forwarding database to send frames across network segments. Bridges have two effects on Ethernet LAN. Raise the bandwidth and they separate collision domains. In an unbridged Ethernet network, the total capacity, which is 10 Mbps, is shared among all stations with a frame to send. The stations share the bandwidth of the network. If only one station has frames to send, it benefits from the total capacity. But if more than one station needs to use the network, the capacity is shared. For example, if two stations have a lot of frames to send, they probably alternate in usage. When one station is sending, the other one refrains from sending. We can say that in this case, each station on average sends a rate of 5 Mbps. In an unbridged Ethernet network, the total capacity 10 Mbps is shared among all stations with a frame to send. The stations share the bandwidth of the network. If only one station has frames to send, it benefits from the total capacity. But if more than one station needs to use the network, the capacity is shared. For example, if two stations have a lot of frames to send, they probably alternate in usage. When one station is sending, the other one refrains from sending. We can say that, in this case, each station on average sends a rate of 5 Mbps. The bridge can help here. A bridge divides the network into two or more networks. Bandwidth-wise, each network is independent. For example, we have 12 stations in a network. In the top figure, without bridging, 10 Mbps is divided by 12. If the bridge is used, the network is divided into two. Each network has a bandwidth of 10 Mbps divided by 7. The bridge acts as a station in each segment. Another advantage of a bridge is the separation of the collision domain. You can see that the collision domain becomes much smaller and the probability of collision is reduced tremendously. Without bridging, 12 stations contend for access to the medium. With bridging, only 3 stations contend for access to the medium. The idea of a bridge LAN can be extended to a switch LAN. Instead of having 2 to 4 networks, why not have N networks, where N is the number of stations on the LAN. In this way, the bandwidth is shared only between the station and the switch. In addition, the collision domain is divided into N domains. A layer 2 switch is an N-port bridge with additional sophistication that allows faster handling of the packets. Evolution from a bridge Ethernet to a switch Ethernet was a big step that opened the way to an even faster Ethernet. One of the limitations of 10 base 5 and 10 base 2 is that communication is half duplex. A station can either send or receive, but may not do both at the same time. The next step in the evolution was to move from the switch Ethernet to full duplex switch Ethernet. The full duplex mode increases the capacity of each domain from 10 to 20 Mbps. Note that instead of using one link between the station and the switch, the configuration uses two links, one to transmit and one to receive. In full duplex switch Ethernet, there is no need for the CSMA/CD method. In a full duplex switch Ethernet, each station is connected to the switch via two separate links. In the 1990s, some LAN technologies with transmission rates higher than 10 Mbps, such as FDDI and fiber channel, appeared on the market. If a standard Ethernet wanted to survive, it had to compete with these technologies. Ethernet made a big jump by increasing the transmission rate 100 Mbps, and the new generation was called the Fast Ethernet, the standard of 802.3u. The designers of the Fast Ethernet needed to make it compatible with the standard Ethernet. The MAC sublayer was left unchanged, which meant the frame format and the maximum and minimum size could also remain unchanged. By increasing the transmission rate, features of the standard Ethernet that depends on the transmission rate, access method, and implementation had to be reconsidered. The goals of Fast Ethernet can be summarized as follows. Upgrade the data rate to 100 Mbps, make it compatible with standard Ethernet, keep the same 48-bit address, keep the same frame format, keep the same minimum and maximum frame lengths. We remember that the proper operation of the CSMA/CD depends on the transmission rate, the minimum size of the frame, and the maximum network length. If we want to keep the minimum size of the frame, the maximum length of the network should be changed. The Fast Ethernet came with two solutions. The first solution was to totally drop the bus topology and use a passive hub and star topology, but make the maximum size of the frame 250 meters instead of 2,500 meters. This approach is kept for compatibility with the standard Ethernet. The second solution is to use the link layer switch with a buffer to store frames and a full duplex connection to each host to make the transmission medium private for each host. In this case, there is no need for CSMA/CD because the hosts are not competing with each other. A new feature added to Fast Ethernet is called auto-negotiation. Auto-negotiation allows two devices to negotiate the mode or data rate of operation. We can summarize its goals as follows. To allow incompatible devices to connect to one another. For example, a device with the maximum capacity of 10 Mbps can communicate with a device with a 100 Mbps capacity. To allow one device to have multiple capabilities. To allow a station to check a hub's capabilities. Fast Ethernet is designed to connect two or more stations. If there are only two stations, they can be connected point to point. Three or more stations need to be connected in a star topology with a hub or switch at the center. It has three implementations, 100 base TX, 100 base FX, and 100 base T4. Manchester encoding needs a 200 mbaud bandwidth for a data rate of 100 Mbps, which makes it unsuitable for a medium such as twisted pair cable. For this reason, the Fast Ethernet designers sought some alternative encoding and decoding scheme. However, it was found out that one scheme would not perform equally well for all three implementations. Therefore, three different encoding schemes were chosen. Here is the summary for Fast Ethernet. The need for an even higher data rate resulted in the design of the Gigabit Ethernet. The IEEE committee calls it standard 802.3z. The goals can be summarized as follows. Upgrade data rate to 1 gigabits per second. Make it compatible with standard or fast Ethernet. Use the same 48-bit address. Use the same frame format. Keep same minimum and maximum frame lengths. To support auto-negotiation as defined in Fast Ethernet. Gigabit Ethernet is designed to connect two or more stations. If there are only two stations, they can be connected point to point. Three or more stations need to be connected in a star topology with a hub or a switch at the center. Another possible configuration is to connect several star topologies or let one star topology be part of another. Gigabit Ethernet can be categorized as either a 2-wire or a 4-wire implementation. The 2-wire implementations use fiber optic cable or STP. The 4-wire version uses category 5 twisted pair cable. Here shows the encoding and decoding schemes for the 4 implementations. Gigabit Ethernet cannot use the Manchester encoding scheme because it involves a very high bandwidth. The 2-wire implementations use an NRZ scheme, but the NRZ scheme does not self-synchronize properly. To synchronize bits, particularly at this high data rate, 8B/10B block encoding is used. Here is the summary for Gigabit Ethernet. In recent years, there had been another look into the Ethernet for use in metropolitan areas. The idea is to extend the technology, the data rate, and the coverage distance so that the Ethernet can be used as LAN and MAN, or Metropolitan Area Network. The IEEE committee created 10 gigabit Ethernet and called it Standard 802.3ae. The goal of the 10 gigabit Ethernet design can be summarized as follows. Upgrade data rate to 10 gigabits per second, make it compatible with standard, fast, and gigabit Ethernet, use the same 48-bit address, use the same frame format, keep same minimum and maximum frame lengths, interconnect LANs to MANs or WANs, make Ethernet compatible with frame relay and ATM. 10 gigabit Ethernet operates only in full duplex mode, which means there is no need for contention. CSMA/CD is not used in 10 gigabit Ethernet. Four implementations are the most common: 10 gig base SR, 10 gig base LR, 10 gig base EW, and 10 gig base X4. Here is the summary of the 10 gigabit Ethernet. This ends Module 16. Thank you.